SwayamPrabha. Digital India. Educated India.
Let's go to the next one. Continuity. Okay, so function. So let's look at this. Let's think of let f be this function, and I'll think of it as a function of n variables taking real values. Okay, it can also be a vector function. It's not very hard to extend this to vector functions. Okay, it's a function that takes from Rn to R. That means it's a function of n variables. And the eventual value that it outputs is a real number. Right. Now, we say f is continuous at a point x in Rn if the following holds. If for every epsilon greater than 0, there exists a delta greater than 0 such that so we say f is continuous at a point x in Rn if for every epsilon greater than 0, I can find a delta greater than 0 such that the difference fy minus fx, if I look at it in absolute value, is no more than epsilon for all y's that are within a delta radius ball of x. So the challenge is thrown in this way. You set how close you want your function value to be. That's your epsilon. You throw me an epsilon, and the challenge is that I will be able to find for you a delta such that if I look at the function values in the delta radius ball around x, okay, look at y's that lie in a delta radius ball, look at these y's that lie in a delta radius ball around x, then the function values f of y are no more than plus minus epsilon from f of x. Okay. Fy minus fx is at most epsilon in absolute value. If you can do this, all right, then we say that the function is continuous at the point x. So we say the function is f is continuous at x, continuous simply. So we say f is continuous if it is continuous at all points. So there is another way of, now this is a somewhat complicated definition because it is posed in terms of this kind of a challenge. There's another way there's another equivalent way of writing this, which is the following, which is using the language of sequences. So suppose if I have, so we say that f is f is continuous we say that f is continuous at x if suppose you take any sequence xk like this that converges to x, take any sequence that converges to x, then along that sequence you look at f of xk and look at the sequence f of xk, its limit should be equal to f of x. So, in the language of sequences, what the continuity definition is basically saying is you take any sequence of uh, of points xk in the domain of the function, domain space of the function, and look at the sequence of values that get generated in the range. Then that sequence of values is itself a convergent sequence which converges to the value of the function at that. So, another in effect what it's saying is limit of f of xk is equal to f of limit of xk. So, the limit basically jumps inside the function, the evaluation of the function. This is what we mean by continuity. Okay, now this then brings us back to optimization. So, I had told you that I had shown you through Queen Dito's problem why it is actually why we can't take for granted the existence of a solution to an optimization problem, because if a solution does not exist, you can get all kinds of absurd conclusions just by arguing inductively without checking the existence. So, we need a way of checking for the existence of a solution that does not entail finding a solution in the first place. Okay. Without finding a solution, you should be able to be guaranteed, rest assured that the solution at least exists. Then you can go about finding it if you want to. Right? So, that is what is guaranteed by this theorem of Weierstrass. So, for me to write Weierstrass's theorem, we should first write out what we mean by an optimization problem formally. So, the way I stated the optimization problem previously was this: is that we are looking for you have a function like this, say a function from Rn to R, suppose, and you have a set S which is a subset of Rn. And what we want is a x star in S such that f of x star is less than equal to f of x for all x in S. Correct. Now, effectively, what we want is this. If you look at the set of values that f takes over the set S, look at the set of values that f takes over the set S. So, f x such that x belongs to S. Look at this set. What we want is effectively the infimum of that set. We want we want the greatest lower bound on that set, because f of x star is the least possible value of f in this particular set, right? But then there is this is the but when you think, if you think of it this way, this creates a the following question: how do we know? We know that the infimum exists for every bounded set. An infimum exists thanks to completeness axiom. But the completeness axiom does not tell us that the infimum is of the form f of x star for some point x star in the set. So, how do we know? So, this quantity exists as a real number, but how do we know? Does there exist an x star in S such that f of x star equals this particular thing? Is clear? So, these are two. This brings us to two separate questions. One is, when is the infimum itself finite? The second is, when is there a matching? When is that infimum actually achieved by a point in the set? Okay. So, if there exists such an x star, we say the, if so, we say the infimum is attained by x star. Okay. In that case, it is both. So, if the infimum is not attained by x star, then it is not meaningful to look for such an x star. It is not present in the set of alternatives that you are searching over. But it is meaningful nonetheless to look for the infimum of f nonetheless. That is meaningful, although the x star, finding the x star itself may not be meaningful. Let me give you an example. Let's look at this function here. Okay, I have this function on reals. So this is the domain of the function. Here I am plotting its values. So the function looks like this. It's decreases up till this point, say suppose point A. Now at point A there is a jump discontinuity. At point A, its value is actually here, not here. So the value of the function at A is this bold dot here, and then from here it increases, suppose linearly like this. So now this is my function here, plotted out here. My S is just real numbers. So can someone tell me what is this? What is this? You are tempted to say f of A, but then f of A is this, and that's certainly not the minimum value of f, right? So what is, so it's meaningful to talk. So what is this particular thing? This particular thing is this point here, the point to which the function tends to from the left, the value of the function to which it tends to from the left. But there is no point in the domain where it takes that particular value. The best bet was A itself, but for A the value is up, is jumped up. There is no point in the domain for which this thing is attained, right? So this limiting value is attained. So this is the case where, as I said, this quantity exists. This one exists. It exists and is finite. It's some finite number. It is this height here, but there is no x star. Okay. So this is a case where the infimum exists but is not attained. So this is equal to this height. Let's take another example. Look at the function e to the minus x, and suppose s is 0 to infinity. So, e to the minus x, how does this look? At x equal to 0, this is going to be 1, and then it will decrease exponentially like this. Now, what is again question here is again, what is this? What is this infimum? 0, right? After all, that is the greatest lower bound for all the function values of f. So, this is equal to 0, but then what is the x star? What is the x star? There is no finite x star. I mean, there is no number. There is no nothing that we can call as a real number which attains this value x, which gives you this particular infimum value. So, there is again in this case there does not exist an x star such that f of x star equals this infimum. Now, as you can see, this is an issue that you are faced with. Typically, you would start with an optimization problem. You have a domain that is specified in a sort of implicit way. You cannot enumerate every point and check what's happening in the domain. You have a function also whose terrain you don't completely understand. The function is specified in some sort of black box fashion for you. You don't know the full how the undulations are, where the function is higher, where it's lower, where it may have jumps or any of that. With that kind of knowledge, you now need to make sure that none of these kind of cases happen. That there is actually that the infimum is in fact attained, and it is meaningful to look for a solution x star for the optimization problem, right? So, that's what Weierstrass theorem gives you. So, now I will state the theorem. Let S be a subset of Rn, that is closed and bounded. In other words, it is compact. Let f be a function from Rn to R that is continuous. Then f attains its infimum on S. That is, there exists an x star in S such that f of x star equals infimum of f of x as x ranges over x. So, there is such a thing called as, in this case, our notation changes. We are not, then we are not looking at, we don't call it the infimum. In this case, when the infimum is attained, we use the notation minimum. Okay. Is the notation used. to denote that the infimum is attained. Is it clear? Okay. Let me end with one small observation which I made last time also, but I will just make it more concretely. I have been talking about, in optimization, I have been talking about minimizing function, right? Here you are looking at out here, you see, I am talking of fx star less than equal to fx. So, I am looking at values that are lesser than all other values, but that is not, so if you are looking for, suppose you have a function g and you wanted to find, suppose g is a function from Rn to R and you have some subset S of Rn and you are looking for a x star such that g of x star is greater than equal to g of x for all x in S. In this case, the problem you are trying to solve is that of a supremum of this, supremum of g of x as x ranges over S. And the question is whether this is attained by some g of x star. Correct? Now, what this that it's very easy to map this back to the setting that setting that we have considered, where we are looking to minimize rather than maximize. Okay, and that's by simply taking fx as minus gx, identically equal to minus gx. If fx is minus gx, then the supremum of this is simply the supremum of minus fx as x ranges over S, which is, it's easy to show, is the same as negative of the infimum of f. Right. So infimizing f is equivalent to supremizing g. Right. So as a result, without loss of generality, we will just always work with minimization, because that also is very somehow fits very nicely with the convex shape of functions and convex sets and so on.